So, good morning everyone. Welcome to the third day of the São Paulo School of Advanced Science on Climate Change. So my name is Cristiano Chiessi, and I'm based at the University of São Paulo, more specifically at the School of Arts, Sciences and Humanities. And I will be giving 3 hours of a lecture dealing with information from paleoclimate archives. I hope you enjoy. Feel free to interrupt when you have questions, and I'll be glad to answer them. Okay? I know we have a very multidisciplinary audience. I hope to be able to fulfill your expectations. Obviously, very multidisciplinary audience has different expectations. So let me try to fulfill all of them. This will be a great challenge. Okay, so this is the outline of my talk. So I'll start to justify why we need to study past climates when we are interested in climate change. And your interest in climate change is as multidisciplinary as it can be. But I'll try to show you that studying past climates will be very important for all of you. Then I will continue by showing the main paleoclimate archives and where we can extract information from the geological record. Third, I will give an overview of the proxies we use. That is the indirect way we use to reconstruct climate. Most climatic parameters are not recorded in these paleoclimate archives as we are able to record them in the instrumental record. If we are interested on temperature in the instrumental record, obviously we look for temperature values in the meteorological stations. If we are interested in precipitation, we'll look into precipitation values, and so on. But if we are interested in, for instance, temperature and precipitation in the past, and now I'm referring to the geological past, those periods where we do not have instrumental records, we have to rely on proxies. We have to rely on indirect ways to reconstruct those parameters. Obviously, there is uncertainty related to the reconstruction of these parameters. But we are able to quantitatively reconstruct them, and this will be extremely important for us. All right, so we have to rely on proxies. And I'll give an overview of the main proxies we use to reconstruct past climates. And I'll finalize this lecture by showing some paleoclimate records that I consider, in this case, I'm the editor, I consider of great relevance for you. All right, so let's start right now and consider why we need to study past climates. And I'll give you 4 main reasons to justify the need to study past climates when we are interested in climate change. Past climates provide a longer-term perspective than the instrumental record on understanding the controls, magnitudes, spatial-temporal aspects of climate change. This first motivation to study past climates is very well depicted in this plot from the IPCC AR5. So assessment report number 5, released in 2013. This is chapter number 5, information from Paleoclimate Archives. So what we have here is rate of sea level change in millimeters per year for different periods of the past and, let's say, the very recent, the common era. Okay? So let's start with the orange bars. There's a zoom here. So rate of sea level change millimeters per year. You see the y-axis here. We have 1, 2, 3, 4 millimeters. And we have 3 different periods here. We have, let's start here with the right-hand bar, satellite altimetry era. So, within the satellite altimetry era, the mean rate of sea level change in millimeters per year is about 3. If we now consider the whole 20th century, the average rate of sea level change decreases to roughly 2 millimeters per year. Big difference between both. If we consider now the last 2,000 years and take the average global rate of sea level change, we end up with 0.5 or even less than 0.5 millimeters per year. So you see a big deal of change here. Interestingly, if we now go back to this is already out of the instrumental record because we are covering the last 2 millennia. Okay? We don't have instrumental records for the last 2,000 years. But if we go even further back in time, and some information I'll show you here go a lot back in time, hundreds of thousands of years. But I'll show you this is extremely relevant for us. And the first reason why it's relevant is over there. Let's go back to what we call, people working with paleoclimate, meltwater pulse 1A. What is meltwater pulse 1A? Meltwater pulse 1A is a period around 14.7 thousand years before the present. So 14.7 thousand years before the present. And the average rate of sea level change by then was about 45 millimeters per year. So this is absolutely outstanding if we compare to the satellite altimetry era change, average change in sea level. Again, this is outstanding related to the 20th century changes in sea level, and this is obviously even more outstanding if we consider the changes during the last 2 millennia. This tells us that the magnitude, for instance, of possible changes, in this case of sea level, are really high. So we have to take a lot of care on the climate system, because if we are going to face a situation like this one here, wow, this will be a great challenge for adaptation and mitigation. Another example, average glacial to interglacial change. When the Earth goes out of a glacial, for instance, the last glacial maximum, and goes into the present-day interglacial, the average change per year, again, millimeters, is about 15 millimeters per year. So, current rate of mean global sea level change is unusual relative to the last 2,000 years, right? Higher rates, however, occurred, but especially during glacial interglacial transitions, and this is a specific moment of the last glacial interglacial transition. So this is the very first reason that gives a lot of importance on studying past climates. Second, studying past climates allow us to test the accuracy, and this we call validate, of general circulation models by comparing hindcasts to paleoclimate archives. So we use general circulation models to project future climate change. You have definitely seen many projections of future climate change. This could be done for the end of the century. This could be done for even longer time periods. This could be done for the next 1-2 decades. But we rely on these general circulation models, and we have to rely on them. They are extremely important in the context of climate change science and applied climate change science. But how reliable they are? There is a myriad ways to assess the reliability of these climate models. And one, my opinion, very good way to assess the reliability of these general circulation models, numerical models, is to confront the output of these general circulation models when they are simulating, so hindcasting, past climates for those we do know what happened. So we can reconstruct based on our paleoclimate archives, based on our paleoclimate proxies. We can reconstruct past climates so we know, for instance, what the Brazil, as a very specific example here, what the Brazil-Malvinas confluence did during the last 10,000 years. What is the Brazil-Malvinas confluence? The Brazil-Malvinas confluence is the position in the South Atlantic, in the western South Atlantic, where the Brazil current and the Malvinas current converge. These are two western boundary currents in the South Atlantic that come together around latitude 38 degrees south. This is one of the most energetic regions in the world oceans. There is a huge gradient in sea surface temperatures across the Brazil-Malvinas confluence. The position of the Brazil-Malvinas confluence is of great relevance to the climate in southeastern South America. The position of the Brazil-Malvinas confluence is of great relevance for CO2 exchange between the oceans and the atmosphere on that portion of the western South Atlantic. And we reconstructed the position of the Brazil-Malvinas confluence during the last 10,000 years. And this is what we did based on marine sediments and the isotopic, oxygen isotopic signature of planktonic foraminifera. I'll give you many details about this later on when I talk about first the archives and second the proxies. But for the moment, it's important for us to see this Y scale here. This is degrees of latitude, okay? And this, the curve here shows the latitudinal deviation of the Brazil-Malvinas confluence from its modern position. Okay, so 0 is modern position, and what we see here is the deviation. So, for the last 10,000 years, here we have the present, and here we have 10,000 years before the present, so Ka, okay? What we have seen is a southward migration of the Brazil-Malvinas confluence until around 5,000 years, and then there is a stable or return to its modern position. There is gradually, and there is a peak of northward migration around 1,500 years. Good. So this is a reconstruction, extremely robust, based on paleoclimate archives, based on paleoclimate proxies. But then we took CCSM3, an IPCC class general circulation model. And we run the CCSM3 for the last 10,000 years to check what was happening on that area during the same time interval. And interestingly, the model shows a very similar trend from 10,000 years before the present until roughly 5,000 years before the present. So, proxy inferred, top, and model southern westerly winds. I'm not talking about Brazil-Venus confluence, I'm talking about southern westerly winds. In this case, the position of the Brazil-Venus confluence is controlled by the southern westerly winds. So, proxy inferred and modeled southwesterly wind shifts. This is model, this is proxy. Compare qualitatively, so the models are doing a very good job in this case. But qualitatively, because the model underestimates the variability by 1 order of magnitude. If you look now to this scale here, you see that the maximum range is plus minus 0.2 degrees of latitude. And we are talking here about plus minus 1 degree of latitude. So it's basically an underestimation of 1 order of magnitude in the long-term change of this very specific feature of the climate system. So, the underestimated natural variability implies a substantial uncertainty in model projections of future southern westerly wind shifts. And, by the way, southern westerly winds are shifting south as global warming progresses. And projections may be highly underestimated based on these results here. So, past climates allow us to test the accuracy of general circulation models by comparing hindcasts, like this one here, to paleoclimate archives. Third, past climates provide long records of natural climate variability that allow a clear understanding of natural climate variability and decoupling natural from anthropogenic variability. This is extremely relevant. When we study the instrumental record, we have a coupled signal. A coupled signal that is forced by both natural forcings and anthropogenic forcings, right? But how to decouple those two types of forcings? This is not an easy job. There are different initiatives to decouple. Many of them are extremely valid and important, and this is one of them. Let me give you an example here. So here we have temperature anomalies for different regions in the world, like the Arctic on top, Europe, Asia, North America, Western Atlantic Ocean, Western Pacific, Indian Ocean, Australasia, South America, and Antarctica. Here we have time going from left to right, from 1,500, from 1,500 to 2,000. Obviously, this is all reconstructed based on paleoclimate archives. And this, the black bar, marks the moment on each record where warming increased. And what we can see is that instrumental records that span roughly 100 years, so they'll go back to 1900, or even less than that. In many situations, they are too short to comprehensively assess anthropogenic climate change. Even anthropogenic climate change may not be appropriately assessed on instrumental records, because in some regions, about 180 years industrial era warming has already caused surface temperatures to emerge above pre-industrial values. So this is an example, Western Atlantic Ocean, where the statistically assessed point of where surface temperatures emerge from pre-industrial values goes back 180 years. And we do not have this 180 years of instrumental records. So past climates provide the necessary long records of natural climate variability to allow a clear understanding of natural climate variability and decoupling natural from anthropogenic variability. And this is an example. And now, the fourth and last motivation to study past climates. So past climates provide detailed records to understand the role of climate change on ecosystems and society. And here I have the following example. This is a compilation from Araújo and co-authors about archaeological ages for central Brazil. So the higher the bar, the larger the number of ages. Basically, radiocarbon ages and stimulated luminescence ages. And we have beams here going from 12,000 years before the present to the present. And as we can see, there is an increase in the number of ages peaking around 8 to 7,000 years before the present in central Brazil. And then a decrease in the number of ages, archaeological ages, and a major increase towards the present, if you want. And why is there a major decrease in the number of archaeological ages during what we call the mid-Holocene? So Holocene is the last 11.7 thousand years before the present, and this is the mid-Holocene. So late Holocene, and from 8 to 11.7 is early Holocene. So why is there a major decrease in archaeological ages in central Brazil? What happened to these populations that once occupied central Brazil? This is a good hint of what happened to these populations. This is a compilation, so every dot you see here is a paleoarchive. It's a paleoclimate archive where paleoclimate proxies have been applied to reconstruct hydroclimate. In red means that the mid-Holocene was drier than the late Holocene. In blue means that the mid-Holocene was wetter in relation to the late Holocene. And so what we see, despite the lack of data in some areas, is a major cloud of red dots around central Brazil. These three blue dots are located over northeastern Brazil. And the color shading behind, also in red and blue, shows PMIP3, CMIP5. Precipitation anomalies. What is PMIP3, CMIP5? PMIP3 is paleo modeling runs to simulate, to hindcast climates of the past. And coupled to the CMIP5 exercise on climate modeling. So what we see in an ensemble from many PMIP3, CMIP5 models is that indeed most of, in this case Brazil, was drier, you see here the red, during the mid-Holocene if compared to the late Holocene. Indeed, this is what our paleoclimate archives show, and what may have controlled the depopulation of central Brazil during the mid-Holocene. So, past climates provide detailed records to understand the role of climate change on ecosystems and society in this case. The justification about the importance of paleoclimate studies in the context of climate change is huge. And by chance, last issue of Nature Geoscience had a commentary from Richard Pancoast from Bristol University that exactly addresses this issue, namely the huge importance of paleoclimate studies on the context of climate change. So, reconstructions of Earth's past climate are much more than benchmarks for climate models, as addressed by Richard Pancoast. Very recent, as you can see here. So, online was published 26th of June, but the printed version was released 2 days ago. He argues, and I definitely agree, that they also help us to comprehend risk by providing concrete narratives for diverse climates. Good. Paleoclimatology, paleoceanography, so the science of past climates, is extremely interdisciplinary, as the audience is. So we have experts working on archaeology, climatology, ecology, environmental chemistry, geomorphology, glaciology, limnology, paleontology, palynology, oceanography, pedology, sedimentology, and volcanology. All of them aiming at the same purpose, namely to reconstruct past climates. Good. So I hope I have convinced you on the importance of studying past climates in the context of more general climate change studies. And now I'll give you an overview of the main paleoclimate archives, namely, where can we go to get the information we need to reconstruct past climates? This is not obvious. Okay, so we can rely on geological slash biological archives that recorded climatic parameters that are interesting to us. Examples: marine sediment cores, tree rings, ice cores, corals, and speleothems. All of them given some conditions may be very good paleoclimate archives. So the archive is the place where we are going to get our information. Take as example a sociologist that is interested, or a historian that is interested on colonization of Brazil. Let's say 1600 history. Where is he going to get his information? On libraries, for instance. He goes to Portugal, example, not only, but example, where he gets the archives of the royal family. And there he makes studies on those archives, what happened in the 1600s. We are interested on the climate of the past, so we need our archives. So our archives are not written. Our archives are impressed in deposits, for instance, sediments, snow, carbonate within caves, or biologically grown archives. All right, a good paleoclimate archive should meet certain criteria. These are two criteria. It's not any tree ring, or tree. It's not any sediment core in the ocean. It's not any speleothem that will be a good paleoclimate archive. Two criteria must be met by these archives in order to make them good paleoclimate archives. So first, its physical, chemical, or biological properties must represent environmental conditions. Obviously, these are the environmental conditions we are interested in. Example, as mentioned before, temperature and precipitation. Obviously, not only temperature and precipitation. We are interested in much more. But temperature and precipitation are two very good examples. Example of a physical property, the size of the grains in a certain sediment core. The size. The larger the size, the stronger the current that transported these fragments. Example, right? I'll give you much more detailed examples of this. Stable oxygen isotopes on the water that forms the ice in ice sheets holds very important information about the temperature controlling snow accumulation on those sites. Temperature is very important to us. Size of the tree rings may relate to the humidity during the main season of growth of this specific tree. And humidity may be directly related to precipitation, and precipitation is a very important environmental parameter. Good. So this is the first criteria that paleoclimate archives must fulfill in order to be considered good paleoclimate archives. Second, because first is not enough. First alone doesn't bring us too far. So second, it must be possible to determine the age of deposition or formation of the paleoclimate archive. So it's not enough for us to know that, for instance, this layer of the ice has a certain stable oxygen isotopic composition that is very much different from this other one and then from this other one, if we don't know when that happened. We have to know when that happened. This is the information we have must be specific in terms of time. In a sediment core, for instance, this is an example of a sediment core. You see the layers here. The topmost layer is the most recent one, and the bottommost is the oldest one in this sedimentary column. If and only if the position here is seasonally related, we can count the layers and assign the year of deposition. Example. I'll go in little more detail on this in the next slides. Similar to the ice core. The deeper layer was deposited much longer than the one closer to the top. So there is chronology involved on these layers. And if we are able to assess in detail this chronology and assign age of deposition or age of formation, we are then able to use this paleoclimate archive, this archive as a paleoclimate archive. Good. So I'll show you now very briefly some features of this main paleoclimate archives I showed before. There's 5 paleoclimate archives I showed you before. So sediments. And I mentioned marine sediments, but it's not necessary. We can have lacustrine sediments. May also be excellent paleoclimate archives. We may have interior sea sediments as excellent paleoclimate archives as well. And we may have the open ocean sediments as very good paleoclimate archives. So sediments are transported as particulate or dissolved matter and deposited in sedimentary basins. They may be continental or marine, forming potential paleoclimate archives. Good. As they deposit, as they make these layers, and these layers are not disturbed, there is a chronology on this. And we may, if we decipher this chronology, and if we are able to assess environmental parameters on the physical, chemical, or biological properties of that sediment, this will be a good paleoclimate archive. Right? Snow. Similarly, as sediments, let's say, accumulates, but in this specific case, obviously in cold regions, to form ice. And accumulation mainly occurs in high latitudes and altitudes, potentially giving rise of paleoclimate archives. And here we have 2 examples of, on the left, mountain glaciers, and on the right, continental glaciers. For instance, in mountain glaciers, accumulation happens at the very top of this basins, if you want, and the flow goes downhill. In continental glaciers, spatial scale is much larger, and accumulation takes place more widespread, and flow takes also place. And in some specific areas, we can take I-scores, and there is a chronology in the deposition. If the properties on that I-score are related to environmental parameters, it may be good paleoclimate archive. Corals, tropical and subtropical clear waters, may be suitable for the growth of corals, and some of them build layered skeletons suitable as paleoclimate archives. Very high temporal resolution we are able to assess when using corals as paleoclimate archives. And tree rings. Trees growth by adding rings to the trunk, and mid-latitude trees under strong seasonality show great potential as paleoclimate archives. There is obviously a chronology on these as well. And if the biological and the physical and the chemical properties of those tree rings are related to environmental parameters, we may use this as a paleoclimate archive. And finally, speleothemes. Speleothemes are these beautiful carbonate elements that grow in caves by the deposition of layers. Here we have a picture of a cave with many stalagmites, and here we have two stalagmites cutted and illuminated in special light so that we can clearly see the layering inside one of or two of these speleothemes. So in caves with stable environmental conditions, the chemical composition of these layers may record regional climate parameters constituting good paleoclimate archives as well. Excellent. So we have 5 main types of paleoclimate archives that must fulfill 2 main criteria in order to make them indeed good paleoclimate archives. There is a question. Do you know where the microphone is? Okay, you can make the question. I have to repeat. Oh, no. Okay, that's the microphone.
Hi. ¿Funciona? Yes.
Yes.
Hi. Good morning. I do not understand how corals can be served like a good paleoclimate archives. Can you explain some more?
Yes, sure.
Just for curiosity.
Sure, sure. Not all kinds of corals, but those that build layered structures are good as paleoclimate archives because, first, the layers, as this type of coral grows, it adds layers, concentrical layers, right? So there is a chronology involved on this, right? The coral growth on known steps, each species with a different, let's say, growth rate, but still known steps. So there is chronology. So this is fulfilled. And second, the material deposited in these layers on these specific corals that are of interest to us is calcium carbonate. So calcium carbonate has obviously calcium, carbon, and oxygen in its chemical composition. And as I'll show you in a few slides, the carbon and oxygen isotopic composition of the carbonate is related to environmental parameters. So far I haven't said that, but you will see that oxygen isotopes are in the water, in this case, oceans, is directly related to temperature and salinity. So we have two important parameters being recorded as the coral grows. So let's say it's now living, it's depositing a layer as they drill. The composition of the water is being recorded in the oxygen. In this case, the physical properties of the water, temperature and salinity, is being recorded by that small, thin layer of carbonate. There are other parameters that we may assess in these corals as well. For instance, magnesium, a different chemical element, may substitute, and strontium, more specifically, magnesium and strontium, may substitute calcium on the carbonate. I mentioned we have calcium, carbon, and oxygen, making the calcium carbonate here. But magnesium and strontium are, let's say, similar to calcium, and they may substitute calcium on the chemical, let's say, structure of this mineral being deposited here. And the extent of the substitution is temperature related. So we determine the tiny amount of magnesium and strontium on the carbonate, and we may assess quantitatively temperature. So this is an example how corals are useful. The interesting point on corals is that they grow very quickly. Well, quickly here, right? Let's take. This is a very good question. I mean, the mean sedimentation rate in the slopes of the continental margins. Slopes go from, roughly now speaking, 100 meters to, say, 3,500 meters. And at some point then starts the abyssal plain, actually deeper than that. But anyway, it's this major depth interval in the continental margins. The mean global sedimentation rate there is 10 centimeters per 1,000 years. So 1,000 years is necessary to deposit this much of sediment. 1,000 years. You can imagine if you have 10 centimeters, how many analyses you can do here. Let's say you can do 10 analyses. Example. So you have 1,000 years of temporal resolution between these two data points you have. Corals, on the other hand, grow much faster, and we can assess much more detailed information on these skeletons. Because we can go in much higher resolution, we can easily analyze every 2 millimeters, every 1 millimeter on this. Because we put this hard, this is considered as mineral, so we put this on a specific sampling device, and we can go in very small steps, and we can extract carbonate in, let's say, 2 millimeters spacing, so we can reconstruct past climates in much higher temporal resolution. It doesn't mean that marine sediments are not good. And sorry, I have to. I made a small mistake here. 10 centimeters per 1,000 years exactly is the mean deposition rate. So if we have every 1 centimeter, we have 100 years of temporal resolution. Okay, good. This was small. Let's avoid the misunderstanding. Good. But still, the temporal resolution we get from corals is much higher. We go easily on interannual variability in corals. So we can assess El Niño Southern Oscillation, for instance, easily with corals. Assess El Niño Southern Oscillation with marine sediments. El Niño Southern Oscillation has a mean, the main mode of variability between 2 and 7 years, right? Assess climate variability within this mode of variability is not very simple with marine sediments, for instance, because they integrate longer time periods. On the other hand, they go much longer back in time as compared to corals, where we have small snapshots. We have 200 years in one coral, 100 years in the other. And here we may cover 10,000 years, 20,000 years, 300,000 years easily with a sediment core. In 100 years resolution, mean resolution in the slopes, just to make sure we got the right figures. Okay, good. So corals, trees, and stalagmites. Good. And if we go into a little more detail, yes, go ahead. I mean, is it possible to make a microphone reach that place?
Thank you, Professor. I have a question. Do you know if stromatolites can serve as also as paleoclimate archives?
Sure they can. Yeah, stromatolites are good paleoclimate archives, but as they were built much longer back in time, the control on stromatolite deposition is not as well known as, for instance, the corals that we can observe right now living in the modern oceans, typically stromatolites, okay? But they can be used as paleoclimate archives. Yeah. So let's now go a little more detail into marine cores. So marine sediment cores, how we get them. So we need big research vessels. These are three examples. Research vessel Meteor, research vessel Marion Dufresne, and research vessel Joyce Resolution. These are three different research vessels that allow at least four different types of coring. One is gravity coring. So this is an image of gravity coring. It's relatively simple. So we can get up to 12-meter long cores. There's virtually no water depth limitation. It's relatively easy to operate, high efficiency, large diameter of the sediment column that we recover, usually 12 centimeters. And we don't need that much ship time. And I'm mentioning here short ship time because ship time is very expensive. So if we don't need that much ship time, it's an advantage. Example of a gravity core that was raised on board, cut in 1 meter long sections, and sliced into halves, working half and archive half. You can see the nice layering on the sediment core, meaning that there is no disturbance while coring. Great. So this is if chronology can be established, and if the properties here are related to environmental parameters, it can be a good paleoclimate archive. Another example, giant piston coring or Calypso coring, typical of Marion Dufresne, but not exclusive of Marion Dufresne. We get up 65-meter long cores, no water depth limitation as well, relatively complex operation, medium to high efficiency, large diameter as well, and short ship time is necessary. We get much longer cores. This is a big difference. There is a specific mechanism, a trigger mechanism that sucks the sediment, so we can get much deeper in the sediment column. And for a given sedimentation rate, we can go much deeper back in time while using this device. Example here, pictures of Calypso coring in Marion Dufresne. You see here the very long tube. You see the white tube here that was pulled out of the iron coring device. This is a PVC tube. Good. As we did for the normal gravity coring, you cut in 1 or 1.5 meter long sections, and you split in two halves, and then you can sample this core, obviously keeping a very good track of the stratigraphic position of the samples. And on Joyce resolution, There's a major step from these two first coring devices to what is now drilling device, ship-based drilling device. This is now the first that drills into the sedimentary column, and not only sedimentary column, but hard rocks if they are there in the ocean. So we can go down hundreds of meters. There's no water depth limitation. I mean, roughly speaking, highly complex operation now. A lot of ship time is necessary, so it's extremely expensive. Medium to high efficiency, small diameter. Okay, example of sections of drilled cores and on board being analyzed. And the fourth possibility is also a drilling device, but it's a drilling device that you deploy to the bottom of the ocean. You don't do drilling from the deck of the ship. You do drilling directly at the bottom of the ocean. You see, there is the ship, and this is the drilling device, deployed at the very bottom of the ocean. And then you start drilling there. So up to 70 meters long cores, operation between 200 and 2,000 meters, this specific one, the MEBO, medium to high complex operation, medium to high efficiency, small diameter, long ship time as well. Good. So this is two images of this drilling device being deployed, just as an example. And now, I'll go to a selection of paleoclimate proxies. Let us just go back 2 steps. Say, why to study paleoclimates? I gave 4 reasons why it's necessary to study past climates. And then I show you the main paleoclimate archives. They are 5. Sediments, and in this case, typically marine sediments, but also lacustrine sediments may come into question. Tree rings, ice cores, speleothemes, and corals. Good. These archives must fulfill 2 main criteria in order to be considered good paleoclimate archives. First, their physical, chemical, and biological biological properties must be related to environmental properties that are of interest to us. And second, we must be able to establish a chronology. We must know when those reconstructed features happened in time. And now I will exactly address how environmental properties may be recorded in paleoclimate archives. Namely, what are the paleoclimate proxies that we may assess in paleoclimate archives in order to reconstruct past climates? I mentioned before, its physical, chemical, or biological properties must represent environmental conditions. Good, so let's now check this physical, how this physical, chemical, and biological properties are recorded, or do record environmental parameters that are of interest to us. Example, so we first sample the core. So this is a 2 centimeter spacing sampling on a marine sediment core. And as soon as we have the samples, we may, in this case, in marine sediment cores, we may see that we have 2 basically different groups of components on that material. And these 2 groups of components may be analyzed. One we call autochthonous, and the other we call allochthonous. So autochthonous is those particles that have been produced, if you want, in this case for marine sediments, on the water column or at the bottom of the ocean. Particles that have been produced there. If they have been produced there, they potentially record conditions from that specific place. Good. So we will use these particles. We will analyze these particles if we are interested on the environmental parameters on that site. But the interesting thing on for instance, marine cores, is that there is a big deal in different extents, obviously, of alloctonous material. So alloctonous material is a material coming from different places, deposited there. What kind of material may be deposited in a certain marine sediment core that was not produced in the water column or at the bottom of the ocean? For instance, sediments transported by rivers. So rivers transport sediments delivered to the oceans, and these sediments get deposited at some point in the oceans, right? This material may come from far away. Take big drainage basins, take the Amazon basin. Thousands of kilometers, a certain sediment particle coming from the Andes may travel all the way and be deposited in the Atlantic Ocean. May not, but is today being transported and being deposited. Smaller drainage basins is the same. The winds transport a great deal of particulate material that gets deposited in the oceans. Not only in the oceans, but also in the oceans. So this is the kind of alloctonous material I'm referring to. And they, if we analyze these particles, they have information from far away. And this is very important, not to confound, let's say, local information from distal, proximal from distal. Okay? And the nice thing on marine sediment cores, as example, is that we are able to reconstruct both marine, local, let's say, features, and at the same time, distant features on the very same layers. And this is a major advantage because synchronizing different archives has to rely on good age models. We have to have good chronology. Let's say we have, example now, we have a speleotheme recording changes in precipitation in a certain place, and we have a ice core from a distal site recording changes in atmospheric circulation on that position. And we want to compare the changes in precipitation as reconstructed based on this speleotheme with changes in atmospheric circulation reconstructed based on this ice core. The only way to compare both is to rely on the chronology of this record and this record. And then we synchronize both of them based on the chronology. But chronology has uncertainties. And so we will be adding two uncertainties together. On marine cores, depending on the situation, obviously, we may have both. We may have marine, the conditions in the oceans, and the conditions from far-field sites recorded on the very same archive without the need to synchronize the chronology. This is just an example. Okay, so here we have examples. It's not extensive, but it's a limited example of autochthonous particles that may be present in marine sediments, in this case, planktonic foraminifera, coccolithophorids, radiolaria, diatoms. These are all organisms being produced in the water column or at the bottom of the ocean. And on the other hand, we have examples of alloctonous sediments. It's not extensive, it's just example. We have different kinds of minerals that were transported from far-field sites to a specific location. So now I'll run into a selection of examples of proxies that we commonly apply in paleoclimatology, paleoceanography to reconstruct environmental parameters. So, major elements in bulk sediment. So, bulk sediment in this case, marine bulk sediment. So, we can relatively easily analyze the chemical composition of the sediment. And here, I'm talking about everything together. Bulk sediment. We are not splitting these two phases. Okay? And based on all these black dots that you see here in the Atlantic Ocean, we analyzed, for instance, iron content, iron concentration, calcium concentration, aluminum concentration, silicon concentration. And we plotted them here as ratios. In this case, left-hand plot iron to calcium, logarithmic, and right-hand aluminum to silicon. And what we realized, for instance, in the iron to calcium ratio, here's the scale, it's logarithmic, that's the reason why we have negative values as well, is that we have much higher values of the ratio close to the continental margins, right? And look at the pink and blue, pinkish and bluish, dominating the central part of the ocean, is very low iron to calcium. A very low iron to calcium, well, it's a ratio, so it can either be a lot of calcium or too less iron in terms of absolute concentrations, right? And well, what this tells us, it tells us that iron is basically coming from the continents, and calcium is basically being produced autochthonously, so in the water column. Thus, in places where we have mid-Atlantic ridge, far from the continental margins, where we do not have the input of sediments from the continents, we have a lot of calcium, relatively low. And close to the continental margins is the opposite. We have a lot of iron. Iron is coming in the allochthonous phase, and calcium is the autochthonous phase. So if we use then sediment cores located close to the continental margins, we can assess how strong the discharge of a certain river was in relation to marine productivity. This is a great deal if we are interested in extreme events, if we are interested in in erosion, rates of continental erosion. These are all extreme events of precipitation and erosion, two major topics in climate change science. So by using this ratio, we can assess changes in extreme events and assess changes in continental erosion through time. Good. And what about aluminum silicon? If we observe the pattern of South America, for instance, what we can see is that we have much higher this reddish and orange colors here close to the equator and the tropics, aluminum silicon, right? And as we progress towards the south, there is this beautiful rainbow of colors going to the pinkish, right? It's very gradual and clear. This shows that, well, it's a ratio, so we don't know if it's if it's a lot of silicon or not much aluminum. In the other hand, here we don't know if it's a lot of aluminum and not too much silicon. But the calculated fluxes, we can do this and we did this, shows that here we indeed have a lot of aluminum being deposited and here we have a lot of silicon being deposited. And the ratio of aluminum to silicon, in this case, particularly from the equator in the slope until 3,500 meters water depth, to this latitude here where we do have a major change, is basically related to the type of weathering on land. And what is weathering? Chemical weathering in this case. Chemical weathering is the process that decomposes rocks and builds sediments out of rocks. in chemical weathering is more intense in higher temperatures and high precipitation climates. Very, very briefly now. And obviously, we have much more intense weathering in this portion of South America than in this portion of South America. Because here we have much higher temperatures and much more precipitation than here. And this is reflected in the chemical composition of the sediment. So now wonder if you have a sediment core someplace here, going back 300,000 years, just an example out of the blue, could be 10,000 years, and you analyze aluminum to silicon, and we can see how chemical weathering changed in the past. And chemical weathering in this case is related to temperature and precipitation. So we may infer changes in temperature and precipitation. Good. Grain size distribution in the terrigenous fraction. Now we only take what is coming from the continent. We exclude all the autochthonous material. And interestingly, what we can see is that the size of the particle is related to the current speed. So as current speed increases, the size of the particle increases in micrometers here, in centimeters per second. Oh, this is great. So we can infer about the speed of a bottom current in the ocean, for instance. And this is very important. So the grain size distribution of the terrigenous fraction is giving us information quantitatively, if we want, or semi-quantitatively, if we don't want to go that far, related to the speed of a certain current. Wow, now a very colorful map again. What we have here is claiming, oh, I knew it was, because I prepared this. So. It's one colorful, one black and white, one colorful, so it changes a little. So what do we have here again in the colorful map is the clay minerals assemblage. What is the clay minerals assemblage? So clay minerals is a certain group of minerals. And we can determine exactly what kind of minerals are there. Examples of clay minerals are kaolinite, chlorite. You don't have to, it's just that you have seen this once. Smectite, elite, examples of clay minerals. These clay minerals are, most of them, produced during weathering, during the alteration of primary rocks exposed in the continents under environmental influences. The primary minerals, they change, they react, and they build up clay minerals in very general terms. And what we can see, for instance, is that of tropical South America, and also equatorial, if you want, South America, and equatorial Africa, kaolinite is the major clay mineral being produced by weathering. It's a clay mineral that has a lot of aluminum. On the other hand, clay minerals being produced in subtropical to tropical latitudes in both continents. Main example, smectite. Smectite has not that much aluminum and a little more silicon. So this relates to the type of weathering, very intense chemical weathering in the equatorial regions of those both continents, and slightly less intense weathering conditions at subtropical and tropical latitudes of both continents, producing smectite and other clay minerals like elite. Out of Antarctica, for instance, there's also weathering going on, but mainly physical weathering, no chemical weathering. Okay? So particles are being just broken into smaller pieces, basically. We have a lot of chlorite. Note that we do not have kaolinite at all coming from Antarctica. You see? there is here input of elite, chloride, chloride, smectite, chloride, elite, iron, magnesium, elite, but not kaolinite. This kaolinite is coming from the Indian Ocean, from different low latitude sites. So this is now every place where we have samples and we analyze the kaolinite and chloride ratio. And we can clearly see reddish colors, a lot of kaolinite, bluish pinkish, a lot of chloride. Again, if we have a sediment core at some place here, we may, by analyzing the kaolinite to chloride ratio, we may reconstruct the strength of chemical weathering, if you want. Or, depending on the depth of the water depth of the core, if we are now very deep in the oceans, we may reconstruct the bottom transport of these minerals as exemplified here in these black arrows here. How the very deep currents are transporting these clay minerals being produced either in the equatorial regions or tropical regions or the very high latitudes. Good. Still on the alloctonous particles in marine sediments, we may be able to use neodymium isotopes to reconstruct the source. Where is the material coming from? Because this is very important. Say we have a marine core collected here, close to the Amazon mouth, but not exactly at the Amazon mouth. Is the signal we have here coming from the Amazon, or is the signal coming from northeastern Brazil? Example only. These two places are very different in climate. The Amazon, particularly western Amazon, is extremely wet. Tropical forest, the largest tropical forest in the world, while northeastern Brazil is semi-arid, completely different. Caatinga biome, right? So, is the material deposited here coming from this place or coming from this place? So we may use neodymium isotopes to assess this information. And how we do this, note that the epsilon neodymium composition is neodymium isotopes calculated here in a specific way. Values between minus 13, if you want, and minus 7 are typical of the tropical Andes, the Solimões drainage basin, the Madeira drainage basin, and the Amazon maize stem. While values of around minus 17 are typical of northeastern Brazil. So if we then analyze this specific sediment core, as we did here in two examples, blue for that place and red for this place here, we may reconstruct back in time, as we know the chronology of those sediments, where the material deposited there came from. This is the principle. This is important information for us. Neodymium isotopes are extremely useful. Yeah, hold on a second.
Just a curiosity, I believe, I'm not an expert, but I believe that these guys who take the samples of the ocean layers, they take several samples among, the ocean. So how robust are the sampling in terms of the layers itself, its chemical composition and its position in the layer? Is robust? I mean, if you take a sample here and 10 miles away, or I don't know, a distant, in a distant point, is these layers, do they match?
Mm-hmm. Yeah, this is a very good question. Yes, The answer is yes, they match. It's very robust. And one site's information is confronted to other sites. And kind of an interactive way to build, let's say, what is the climate history of a certain period of interest. Obviously, some sites are more representative than other sites, because these sites that are not very representative, they may be under very specific influences. Open ocean sites are usually representative of larger areas than enclosed basins for obvious reasons. Take as an example, for instance, if we are analyzing oxygen-stable isotopes in carbonates, marine carbonates, and we have a core collected very close to the shore, very shallow waters, okay? And say we have 5,000 years of history on this core. And as I mentioned before, the oxygen-stable isotopes in carbonates is related to temperature and salinity. And let's say, as an example, in this last 5,000 years, temperature did not change it much in that area. It's not covering the instrumental record. It's only covering pre-industrial last 5,000 years. And because this is very shallow waters, it may have been the case that this place was a lagoon 5,000 years ago. Example. In lagoons, salinity may get very high. It's not obligatory, they may get, right? So there, oxygen-stable isotopes would be registering a very specific feature that is not related to open ocean conditions, right? But then if you analyze another core from the slope, so open ocean, for this very same 5,000 years, you may not see this high salinities. So the core close to the shore is recording a very specific environment that is not representative, let's say, for the open ocean, for larger area. So by understanding the specific environment where our archive is coming from, we are able to assign to give a larger or a smaller weight, if you want, to that specific record. But in general terms, paleoclimatologists and paleoceanographers are aware of this and do consider this kind of information while interpreting the records. It's a very important point. So back to neodymium isotopes, and what I mentioned before was neodymium isotopes analyzed on the allochthonous phase. But now let's look to the autochthonous phase, so the phase that was produced in the water column at the sediment-water interface. And there we can also analyze neodymium composition in oxides, manganese, for instance, oxides that deposit in the sediments at the bottom of the ocean as they are sitting there for a certain period of time before getting buried. And there, and all these analyses reflect the composition of neodymium isotopes in the bottom of the ocean, but not on the terrigenous phase. What we can see is there is a clear pattern here. It's not randomly distributed, the colors. What we can see is this reddish and yellow, orange values in the Pacific, also in the Indian Ocean, and in the Southern Ocean. While we make progress towards the North Atlantic, we go towards this greenish and bluish values, much more negative, and here not that much negative. These values here are related to the weathering of younger rocks, outcropping in large amounts around the Pacific Ocean. Instead, around the Atlantic Ocean, we don't have that much young rocks being weathered. On the other hand, we have much older rocks being weathered. And typically, in the North Atlantic, this will give us much more negative values. Later on, if we use this information, we may use this information to assess where a certain deep water mass is coming from. If the deep water mass is coming from the south, in the Atlantic specifically, it has an imprint, and the imprint is this values close to zero in terms of epsilon naught. If the water mass is coming from the north, the deep water mass, we have much more negative values. And I'll show you later on a good example of this that relates to carbon cycle, that relates to how much CO2 was within the oceans during past periods of time. We may analyze also the organic matter on sediments. And we call this in general terms biomarkers, because those I showed before are not biomarkers. And here, specific lipids called GDGTs, very long name, may allow us to reconstruct mean annual temperature. And in absolute values, degrees Celsius. Where are these lipids produced? These lipids are produced by soil bacteria. And they get transported and deposited in lacustrine sediments. They get transported and deposited in marine sediments. So lipids produced by soil bacteria on land, deposited in the ocean. And we may analyze them, all these lipids here, and by doing a ratio of these branched GDGTs, we may come up with mean annual temperature where this bacteria once lived on land. Great, so we can reconstruct temperature on land in degrees Celsius. That's excellent. On other types of lipids, in alkanes, more specifically C29, C31, we may analyze the deuterium and the carbon isotopic composition. So, plants produce plant waxes, and these plant waxes have a lot of N-alkanes, long-chain N-alkanes. And these compounds are extremely resistant, like the branched GDGTs also are. So they get transported and deposited in lacustrine sediments, in marine sediments as well. And we can collect these sediments and we can separate these compounds from other organic matter compounds. And we can analyze the deuterium composition and the carbon isotopic composition. And this is two examples from northeastern South America. As I mentioned before, northeastern Brazil is semi-arid. And the Amazon basin, as you all know, is tropical humid rainforest, basically. And note that in the ocean, and very close to the continent, the composition is very much different in terms of delta D, deuterium. Of northeastern Brazil, we have less negative values, whereas of the Amazon, we have much more negative values. In this case, deuterium is related to precipitation, is related to the amount of precipitation. So we have much more precipitation in the Amazon, leading to more negative values. We have much less precipitation in the Parnaíba, leading to less negative values. Fractionation of deuterium happens in the atmosphere as a certain cloud, if you want, progresses towards the continent, and there is rain out, fractionating the moisture. This produces a great deal of fractionation. So we can, given a certain marine sediment core, we can assess the change in precipitation on land, in this case qualitatively, not quantitatively, based on delta deuterium. On this case, delta 13C is actually related to the photosynthetic path that vegetation on land preferentially takes. If we have C3 vegetation or C4 vegetation, in this case, typically northeastern Brazil, there is a lot of C4 vegetation. This is the photosynthetic pathway, or C3, C4, and CAM. CAM will live for a while. We take only C3 and C4. So C3 occurring widespreadly in the Amazon, and C4 occurring widespreadly in the Parnaíba. And what we can see again is that the delta 13C of this plant waxes change according to, this is core tops, okay, this is modern values. They change according to the input, if Amazon in this case, or northeastern Brazil. Good. Another biomarker, and now not anymore related to far field conditions, but to local conditions. Alkanones are other organic compounds, in this case built by these beautiful nanofossils, these nano particles. These are algae, and these algae produce, among many other compounds, alkanones. And a specific ratio of alkanones, called UK37, is linearly related to sea surface temperature. Great, so as we are able to analyze and calculate this index, we can assess the sea surface temperature of that moment in time when these compounds were produced by this algae living in the photic zone in the oceans. Now we have 10:30, and now we'll make a break until 11 o'clock.